بسم الله الرحمن الرحيم. السلام عليكم ورحمة الله وبركاته. Our experiment for this week is going to be about rotational inertia. And recall that the rotational motion is analogous to the translational motion, such that the moment of inertia I plays the role of the mass, and the torque plays the role of the force, and the angular acceleration plays the role of linear acceleration, and so on. So in the first part, we would like to determine the moment of inertia I for a pulley using a pulley and a block system. The forces that act on the block is the weight and the tension, such that we have the following relation or the following equation for Newton's second law. We have the weight minus the tension equals m times a, where m is the mass of the block. So you can see that the acceleration is in the same direction as the weight. Now, as for the pulley, if we consider a string element, the tension on this element would be directed downward. And if we want to find the torque on the pulley, where the center is the center of the pulley, we can see that the angle between the force of tension and the moment arm is 90 degrees. So we can simply multiply the two to get the torque. So the torque is the force of tension times the radius, not the whole diameter, but only the radius, because we are taking from the center, equals I, which is the moment of inertia of the pulley, times alpha, which is the angular acceleration. And remember also that the linear acceleration is related to the angular acceleration by the radius. Now, if we solve these three equations, we can simply obtain this relation, where I equals mr squared g divided by a minus 1. Now, be careful that m here is the mass of the block, not the mass of the pulley. Now, we rearrange this equation by dividing by r to get the following relation, and we do that simply because we cannot measure r directly using the simulation, as we will see, but we will obtain it indirectly, as we will shortly see. As I said in part A, we will determine the moment of inertia I for the pulley using a block and a pulley system. And in this lab, we will use Boston University Virtual Lab instead of FIT. So in the website, go to the rotation simulations. In part A, we'll do a block and a pulley, and in part B, we will do a rotation of a revolving door. So let's go to a block and pulley. Now go to the simulation and read the instructions. And by the way, the G in this simulation is set to 10 meters per second squared instead of 9.8. So note that and use this value in your calculations. Now, for the mass of the pulley, in my case it's 2 kilograms, and we will start the mass of the block by 0.1, and we will increment it by steps of 0.3. Again, this is my data. You will have your own data in the manual. In any case, so the mass of the block is 2 kilograms, and the mass of the block is 0.1, and the mass of the pulley is 2 kilograms. Now you can read immediately the value of the acceleration and the tension, also the weight, without clicking play. But if you want to see it, this is how it goes. We will need this play button for later in this part. But what you have to do is you have to report or record these values of the acceleration and the tension in this table. So in my case, it's 0.91, and the same for the tension. So in the table, record the value for the acceleration and the tension. Okay. Then increase the value of the mass of the block to 0.4. Again, you will have acceleration and tension. Then 0.7 and so on. Okay. Up to 1.3 in my case. So after you complete the data, you have to calculate I divided by r squared using which equation? Using equation number 6, this one. So we'll go to Excel, copy this table, go to Excel, then paste, apply the formula, equals m times do not forget the star, g, which is 10 in the simulation, divided by the acceleration minus 1. Okay, do the same for the other cells. Now you have to find the average of I divided by r squared. Now we determined I divided by r squared, but remember that our goal is to find I for the pulley. To do that, we need to find the radius of the pulley. So we will use this equation that relates the angular displacement to the time. So we'll find the time using a stopwatch from your mobile phone. We'll find the time that it takes the pulley to complete 1/4 of a turn. So theta is 90 degrees or pi over 2. And by finding the time, we can find the angular acceleration using this formula, since theta initial and the initial angular acceleration is 0. And by finding the angular acceleration and knowing the linear acceleration, we can determine the radius of the pulley. And we'll use the same masses for the pulley and the block as in the previous table. So we already measured the values for the linear acceleration. Simply copy these values and paste them in table 2. Okay. Now open the stopwatch in your mobile phone. You cannot see mine. And go to the simulation. Set the mass of the block to the initial value. Now, what you will have to do, you want to find the time that it takes this reference line to go from 0 up to pi over 2. So you'll have to click play and click start on your stopwatch at the same time and pause the motion when this green reference line reaches 90. Okay, so click start. Okay, so there is some error, but it's expected, and we'll do many runs to minimize this error. So my stopwatch reads 3 seconds. So I'll write 3 seconds. Do another run. So increase the mass to 0.3. Reset your stopwatch, and again do the same procedure. Click play and start at the same time. My stopwatch reads 1.89. Okay. Do the same for 0.7 and 1 and 1.3. So after completing the time measurements, we have to find alpha, the angular acceleration, and the radius. We'll find alpha using this formula, where theta is pi over 2. So when it's multiplied by 2, the numerator becomes simply pi, divided by the time squared. As for the radius, we'll use the equation that's all the way in the top. A equals r times alpha, so r is the linear acceleration divided by alpha. Okay, so copy this table 2, and go to Excel. Paste. So to find alpha, remember that you have to write pi in the numerator divided by the time squared. Do the same for the other values. Then to find the radius, divide a by alpha. As you can see, my estimate for the radius here is slightly off and different from the other values, but to eliminate the error, we'll find the average radius. Okay, then at the end, to find I, we will multiply this value by the radius squared. Okay, So in my case, this is I for the pulley, and so report the value of R in the data analysis section as well as I. Then I have to find the percent difference when the reference value or the estimated value of I is 9. And this completes part A. In this part, we will determine the moment of inertia of a revolving door. And if you do not know what a revolving door is, here is a picture. So we'll use the same simulation website, and you can use this link to go directly to the intended page. So this is a top view of the revolving door, and here is you applying the force in a certain position and a certain force. You can control these parameters. You can change the position, and you can change the applied force. You can also change the parameters for the door. You can increase its mass as well as the length of the door. And by clicking play, you'll see a plot of omega versus t for a simulation run of 20 seconds. And I'll tell you how we can utilize this information to obtain the moment of inertia. Now recall that the torque is in general the moment R times the applied force times sine theta, but since we are considering perpendicular force, the sine theta, sine 90 degrees, is 1. And the torque is I, which is the moment arm, times the angular acceleration. By rearranging, we obtain the following relation. Alpha equals F divided by I times R. We know F and we know R, and using the slope, we can determine I if we plot a relation between alpha and R. But let's use the simulation and the plot of omega versus t that we just have seen to obtain alpha. We know that omega 0 and t0 are 0 in our case. So simply by reading the values of omega and t, we can obtain alpha. And by taking many values of alpha, we can obtain a plot of alpha versus R. And by doing so, and from the slope, we can obtain the moment of inertia. Let's do that. So let's use the same parameters that are given here. Set the force to 5 Newton, the mass of the door to 40 kilograms, its length to 1, and the position of the force to 0.2. And again, this is my data. Use your own. So the initial position of the force is 0.2. We'll change it with certain increments and fill in the table. And this is R. And the size of the force is constant, and it's 5 Newton. And the mass of the door is 40 kilograms, and its length is 1. So by clicking play, we can see that at 20 seconds, omega is almost 0.4 maybe. So go to your table, write down the value of omega, 0.4, and the value of the time, in this case is 20 seconds. And do the same for different R's and see what's omega and what is t. For example, if we set the position to 0.6, you will see in this case that at 18 seconds, omega is 1. So I'll write down for 0.6, omega is 1, and t is 18 seconds. So complete your table. Then go to Excel to make a plot of alpha versus R. How can we obtain alpha? Alpha is simply omega divided by t, because omega 0 and t0 are both 0. Select the two columns. And do the same procedure. By now you should be expert. So add a trend line, display equation chart, and do not forget to write down the information for this plot. We have what? Alpha versus R. also label the axis. So using this slope, you can obtain the value of the moment of inertia by answering the questions in the discussions. Now you can obtain the moment of inertia using another method, using a geometric argument, by using the following relation, where m is the mass of each panel of the door. So in my case it's 40. Use this mass, and L is again the length of each panel of the door, and use this same value. And by doing so, you obtain a reference value or a different value of the moment of inertia, and you can calculate the percent difference between this value and the experimental value you obtained from the slope. And by this, we finish the experiment. Write down a conclusion that summarizes what you did and what you found from parts A and part B.